All right, hello everybody. Welcome to large language models for real world applications. I'm excited to be speaking to you about what I find to be the most exciting topic in all of computing and technology as a whole. From this workshop, I want you to get exposure to some of the main ideas in this new concept, large language models, and how they're used in the real world. So we'll begin with some introductions, and then we'll talk about how language AI is already here. This new form of engineering called prompt engineering. It's a new paradigm of computing that is now emerging. Some tips for more reliable text generation. So you're not just fooled by cherry-picked examples where it can work 1 in 10 times. So how can you get more reliable generations? And then some more use cases, classifications, and search by meanings. Let's begin with some introductions. I have a few of these. I didn't know which one was best, so allow me to go through all of them. And they're not connected, so we're just reset from. So the invention of writing and the printing press led to a flowering of science, literature, and the arts. Might machine understanding of language lead to something similarly grand? Let's skip the second one. OK, this is another one. Let's start from the beginning. Let me tell you a story. I was reading a book a few years ago called The Writing of the Gods. It told a story of the invention of writing, the first symbols that humans invented to represent sound. It was a profound development. I will quote from the book. It says, "The first writing must have come as a surprise and even a shock. People had to stop and wonder what this new thing could be, how it worked, what it was good." Stops there. A couple more. In the early 21st century, computers started to get good at understanding human language. They became so good that people started to realize that it could change the world. This idea has been at the forefront of many investors' minds. And finally, the Renaissance is generally seen as the birth of the modern world, but what we rarely realize is that it was made possible by the invention of writing, the printing press, and the circulation of books. The invention of writing may not seem that important, but it was the most radical technological development in history. It changed the world, the way we relate to our world and our place in it. It is the basis of civilization. And you see, I bring up writing and the printing press, and maybe we can talk about the internet as language technologies that sort of changed human history. And we're talking now with one potential change that changes just how humans work with technology. And that is the language model. In fact, none of these introductions were written by me. These were all generated by a language model. So each one of these 5 was a response to a prompt given to Cohere's language models, and they were generating them. And we'll go over how those were generated. So a language model is a piece of software. It's trained on a bunch of data, and then after that, it's able to do a lot of language processing tasks. A large language model is an even bigger language model that is trained on internet-scale data. So these are hundreds of billions of words or tokens. Some ways to think about how we can get value out of these language models is generation, so they can generate text, classification, so they can categorize an email or a message as either type A or type B. And they can embed things, so translate things from being text into machine language, into representations that capture the meanings in the text in a way that computers can deal with language. And for maybe the first time in history, we're able to do some of these things better than ever before. So text understanding and search. In 2019, Google Brain released a paper about a model called BERT. And 1 year from that, BERT was responsible for about every query in the English language for Google search. And this is a blog post where they called it one of the biggest leaps forward in the history of search. So this is 20 years of of Google acquiring all the data and engineering power, like this single technology is like a tremendous leap forward for how text understanding and search is improved using language models. And then text generation is this new capability. Like we did not have software that can write in a way that is convincing, that you can't sometimes really tell, was this written by a human or was this written by a machine? This is a new capability. If you're paying attention to some of the VC reporting, generative AI is this new theme that captures language models, but as well as image generation models, and as of last week, video generation models. And all of these are sort of supported by language models. One milestone in this development is the transformer. It is the architecture of neural networks that is enabling a lot of these developments. The paper came out in 2017 called Attention is All You Need. And now transformers crush almost every NLP benchmark there is out there. And not just language processing, but it's also going to power image generation. So all of these images that we've seen were generated by this model called Stable Diffusion. You just give it a piece of text, it will generate an image in the style that you choose. And that is powered by a language model sort of working as a part of it to help it understand the language of the input prompt, and then the rest of the system can do the other interesting things, which is generate a very strange image. So language AI is already here, and you have already interacted with it. So if you want to learn a little bit about, let's say, Siri, you go on Google, you put in some keywords, you search for, let's say, Siri tech, and you get a couple of suggestions, maybe your browser as well as your keyboard. When you search, you get this brief about the result, and then sometimes when you click, you get these highlights on the page, which is just like where the answer to your query lies on that page. And I tend to ask people which of these steps you think uses language AI. So if you think one, you can raise your hand. Do you have any for one? I have about 40% of the room is for one. What about two? The same 30%, that's amazing. And three, I have a little bit more here, yes. So it's a trick question. All of them use language AI, and all of them are like language processing tasks. So these two of like suggesting the next word, this is another one, this is a third one. And there's an even more important one, which is between steps 1 and 2, which is how Google was finding for you documents that are similar to this query. We break these down, they're called tasks. So these are some of the task names for these language processing tasks, I guess. So auto-completion is like predicting the next word or the completion. Semantic search is the one that, let's say, powers a lot of Google's search. Text summarization is this one. So this is basically a summary of this Siri Wikipedia page. And then here, this is what's called question answering, where you give it a piece of text, you give it a question, and it will highlight for you where the answer to that question lies. If you use Gmail or some of these email clients, they give you some suggested responses. This is another task called response selection. And so language processing, there's so many tasks. You can spend a lifetime understanding and sort of going through these various language processing tasks, all of them which are now being powered more and more using language models and language AI. It's even more interesting when you include other modalities. So when you extend beyond just text and you add images. And this might be surprising. Like if you've worked with software, like we had capabilities like this since like 2015. So this is image captioning. So this is software that you give an image, it will describe it. If you've worked with software or tried to write code that checks, is this email in the right format? This feels like magic. But we've had this since 2015. But what has happened from 2015 until now? So this is a piece of software in this paper that you give it this image, and it will say, okay, this is a group of people shopping at an outdoor market. There are many vegetables at the fruit stand. Now what we have is something like this. So this is a model called Flamingo from DeepMind that does this visual question answering. So you give it a picture, and it will say, OK, this is a picture of Barack Obama. He's a former president of the United States. So this is the same image captioning. But then you can have a conversation with the model. I don't know if you can read this, but I can read it out loud. So we ask the model, after it gives us the caption, we can say, how many people are in this picture? The model says, there are at least 5 people in this picture. Where was this picture taken? The model says, it was taken in a school. How many mirrors are there? The model says, there are at least 2 mirrors in this picture. What is the person standing on? The person is standing on a rug. And then we correct the model saying, he is standing on a scale. The model says, I think you are right. What is he doing? The next question. He is looking at the scale. Where is Obama's foot positioned? Obama's foot is positioned on the right side of the scale. We ask the model, what happens as a result? The model says, the scale shows a higher weight. Is the person on the scale aware of it? I think he's not aware of it. Do you think that's why the people are laughing? I think so. So this same picture was posted in about, I think, 2012 by a researcher, by Andrej Karpathy, who was like he was leading AI at Tesla, saying this picture makes him depressed because that technology seems so far, like the model will not be able to understand the subtleties of this joke, this practical joke that is happening. And it only took 10 years from that post that we already have these models. Now, a couple of things to be aware of here is one, cherry picking. So how many examples were the model shown that the model was not able to really identify that subtlety? And that's a detail that you might miss if you're just seeing these examples on Twitter. So this idea of cherry picking is an important one to when confronting the results of these models. And the other one is that there's something also subtle here where the prompter is actually sort of guiding the focus or the attention of the model towards the result that we want to do. So, and this sort of emerged as a way of prompting. So we can have models solve more complex problems by breaking it down into a step-by-step. So this became another, let's say, prompting technique called chain of thought prompting. So here we're educating the model a little bit, but then this can actually be used to solve real problems by breaking them into smaller and smaller problems. You also have come across it in products. So if you have Google Photos, if you search for words that appear in the pictures, that sort of OCR is used in that retrieval. So that's one form of, let's say, this multimodal, but also classification. So if you search of a cat, you will get a cat, even if the word cat does not appear in the picture. So this multimodal, say, capability of adding language and images together is already finding its way to products. And so tech companies are racing to sort of build all of these into their products, into the assistant, into translation, into these various products. I promise this introduction was not generated by a model. So my name is J.L. Ammar. I write a blog for about 6-7 years about language models and natural language processing. I have a YouTube channel where I explain some of these concepts. I work at Cohere, which is working to make NLP part of every developer toolkit. That is one of our founders. Aidan is one of the co-authors of the Transformers paper. And what Cohere does basically is provide these language models as a managed service. So you don't have to worry about deployment. You don't have to worry about training or fine-tuning. You have an API. You give it text. You get text back. Or you give it text, and you get embeddings back. We'll talk about what that is. One sort of differentiation of managed versus self-hosting is this famous figure in machine learning where your ML code is just that small part in the middle there, while a managed language model provider would take care of all of these things for you. You can interact with the Cohere models via the playground, so you can do it by API, but also you can get through the playground and just have that text box in the middle. You put in some text, and you get some text generated out. And this is the actual prompt that I use to generate the introductions. And it came through, there's some experimentation. That's why it's called prompt engineering. The first one that you make will not work right off the bat for exactly what you want it to do. And in the beginning, I said, make it a TED talk. So I wanted that sort of grand TED. But then it became a little bit pretentious, so I added that last sentence. So I can just go over a little bit of this. So this is the opening paragraph of a talk titled Large Language Models and the Real-World Applications. Delivered at the conference. It's meant to explain the business applications and problems. So I'm giving the model a lot of the context of what we're trying to do here. And I'm saying, this is the transcript. So what would you imagine the transcript or the opening paragraph or passage would look like? And I'm giving it some of the ideas that I wanted to reflect. So I didn't want to write this, but I'm like, I think this would be a good idea to relate this to language technologies. The point being that these technological developments, like writing and printing press, led to changes like recorded history, like the proliferation of books. The audience is led to wonder what might machine understanding of language lead like. And then I added this. The talk avoided sounding too grand and pretentious. So you have to steer the model a little bit sometimes. And then I got these generations. I got a few of them. So I generated about 8 or 9 of them, and I ended up using 4. So these are the major capabilities. So generation is used for problem solving across a lot of kinds of problems. So it can be used for rewriting, for summarization, for creative writing, which is what we saw here. It can extract things like named entity recognition, but a little bit more contextualized and a little bit more intelligent. I'm really excited about its capability to generate training data to make other types of models work better. Classification, this is another sort of endpoint that Cohere provides. So you can use large language models to classify as either class A or class B. So you can categorize email or messages or any type of text either by topic or by emotional content, or maybe this is for sales, this is for marketing, let's route it to the right people. And then embedding is sort of the most technical of these, which is enables use cases like searching by meanings, like categorizing and clustering things together, and like analyzing text and exploring them. So let's talk about this new form of prompt engineering that we've just discussed. So we have a prompt engineering guide, and some of the first words is, okay, what is a prompt? So that is the input that we get to the model, and then we get a completion, which the model completes. And the model outputs the completion based on the vast amounts of data that it was trained on, so all the text that it saw. The easiest first prompt is to give it a paragraph or 2 paragraphs and then say, in summary, and then the model is sort of trained to give you some, it's not specifically trained for this, but it understands that the probability of what appears after the word in summary and then article is to give you a summary of this article. And this is what's called a few shot, or like a 0-shot example. So the model here is not being trained at all. So this is just a pre-trained model, and you're just making it do useful things for you based on how you shape that text input. No coding required. When you try to create more advanced, or you want to get better results, it's always good to add a task description that explains a little bit of the context of what domain is this in? How are you expecting this text? What kind of audience do you want this text to sort of appeal to? So we have an example here. So you can improve the summary a little bit by saying, this is an article followed by a summary written in an informal language. So this is a task description that is before the actual input that we want to summarize. And this is an important component of any prompt that you engineer in the future. Another really important idea is having examples. So showing the model what kind of output that we want it to create. So, and here you can think about free-flowing prompts. So if you give the model an example, which is, let's say, a short poem, and then example 2 is another short poem, it will continue generating short poems for you. Now, how good they are will depend on how large the model is, how much data it was trained on, how much poetry was in that data, was the model fine-tuned or not. But that's one important concept. So the more examples that you show, you're able to guide the model to do what you want, especially if you also add a task description saying, these are short poems about such and such. Now, you can also do these structured prompts as well, where each example is an input and an output on its own, where it's not just free-flowing, talk like Shakespeare. It's like, OK, I want you to be a classifier, a sentiment classifier. And I will show you 2 examples here. So I will give you one very short review and show you that the sentiment is positive. I'll give you another short review and show you that the sentiment is negative. So you understand that, OK, these are the 2 classes that I can think of. And then I will give you this 3rd example, and I will have you complete the classification. And so this is another one of these main ideas for language models. This is what's called few-shot learning. This one didn't make the cut, but it's my favorite introduction of the bunch. In 1788, 1 year after the United States became a country, 2 of the most significant events in human history occurred within 3 weeks of each other. The first was the signing of the United States Constitution. The second was the first patent for the steam engine. Both of these events have had lasting impacts on the world, and both led to rapid development of a technology that we now know as artificial intelligence. I was absolutely hooked by this. I've never written a hook nearly as good as this. How are they related? What's this one and this one got to do? How do they meet 250 years later to create? I have no idea. But this is a good example of we need to be a little bit suspicious about the factuality of what the model. So I wouldn't have just thrown this out there. I would have to double check. Did these things actually happen on these dates or not? I think they mostly have, but it's very easy for people to come across these models and want them to generate facts for them. And that's not what they do. Let's just treat them as just language, understanding, and sort of language, let's say, probability. But we have better tools for retrieval. And there are more and more technologies of language models that have a retrieval component. They can go search the web or search a database and get the relevant information and use that in the generation. But let's not use language models for factuality. So we have to fact check everything that they do. One very useful prompt pattern is a list. So where you say, this is a list of such and such. And then you give it 2 examples and you have it complete that list. So this is super useful. We'll see examples from research coming up. So that's text generation on the prompt side. There's a lot of useful things to do on the process of generation itself. So one important thing is it's an extension of what we just mentioned, which is not to think of the model as this intelligence that is general. It is very, very narrow, intelligent agent. So it knows just a few things. And no matter how convincing the words that come out of it as output, we should never associate communicative intent to them. So one way that translates into more reliable generation is not to take every output that the model gives us. So we have to think about the generations as candidates. And we give it one prompt, we get, let's say, five different outputs. And then from those, we can select the best or a couple best. It's usually the best if a human goes through that and is in the loop and sort of selecting these. That's always the best way of thinking about this. One way to automate this a little bit is to have this likelihood scoring. So you can generate these 5, you get a likelihood score. The API gives you this in return. So this is the probability of this text. And you can just take the one with the highest likelihood. So that's a way to get better scoring generations. And there's one thing that, let's say, I don't know if you know of Google's Lambda, so it does this. So every response that Google's Lambda gives out is actually, it generates 16 responses and then just gives you the top one of them. And that is one of these tools in this playbook of having better and more reliable language models. So classification is probably the most used use case in industry. It's one of the more really practical applications to use this model. And to developers, I explain it as, you give the model or the system a piece of text, and it will say, OK, this belongs to class A or class B. And then based on that, you can just branch and do different things. When I was learning text classifiers, I wanted a page with a lot of examples of text classifiers. I couldn't find it, but I built one. This is it. So these are 6 examples of text classifiers and what classes they break a text into. So sentiment is the most commonly used one. So you give it a tweet or a sentence or an email, and it will measure how much emotional content is there. Is there emotional content or not? Is it positive or negative? Topic is very useful. So we have tweets, we have customer correspondence. Is this about product A or product B or product C? Is this about this area? Is it about shipping? Is it about... So this is a topic classifier. And all of these can be, they can assign one category to a piece of text, or they can assign it multiples, which is called a multi-label classifier. Spam classification, a lot of spam can be predicted just by the content. Toxicity is another one. So this is so a lot of human contact is now on social media and digital spaces. There's a lot of online harm and bullying that happens in a lot of these. And so toxicity classifiers is one form of these classifiers that tackle this very, very difficult problem for humans and machines both. And if you're comfortable or aware of chatbots, chatbots break into 2 NLP tasks. The main one of them is intent classification. So you get a message or a few messages from a human, and then you try to classify the intent. This person is saying hello, or this person is saying goodbye, or this person is asking about our shipping and handling policy. So it's one of the 2 main ideas behind chatbots. In addition to talking about generation, classification, and embedding, I really love these use cases that use multiple of these. And I think there's a lot of underexplored areas there. This is one area that uses generation to create better classifiers. So this is a data set this is a paper called ToxiGen that generates a lot of examples that can be then used to create better toxicity classifiers. And this is a problem where you don't have enough data because in this specific case, it's about protected groups. So racial groups, for example. Some of them you don't have many positive or many negative sentences or examples targeting that specific group. And that makes building classifiers for that group very difficult. And so this is one way of expanding whatever data set that you have through generating it. And this is basically done through the list prompt that we went through. So if you have 2 examples, you can create 100 more examples just by having that list and having the model generate a few. Classifiers, 2 main ways to use language models to create high-performance text classifiers. We talked about few-shot. So if you only have a few examples or tens of examples, you can try the few-shot capabilities of models. It can take you there. It can produce a reasonable example for you. There's a lot of research about zero-shot. In practice, we always say, if it's an important problem, just label 5 examples, just label 10 examples. I think zero-shot is potentially somewhat of a party trick. So, few-shot is useful. Just give it 2 minutes, label a couple of examples, or but then to get the absolute best classifier that you can get by today's technology, usually you have to go through this process called fine-tuning, which is just continuing to train the large language model a little bit more for your data set. This is what fine-tuning does. We get the stock pre-trained large language model trained on the internet scale data, and then you have your own data set. Either this can be just the writings of Shakespeare, and that creates a custom model that talks like Shakespeare. This can be your classification data set of your text and your classes, and this will lead to your custom large language model that is super focused on your problem. Search by meaning also goes by these other two names. You might have heard of semantic search or neural search. There's a lot of exciting activity here. A lot of it revolves around this idea of embeddings, which is you give a piece of text to this model, it gives you a vector, a series of numbers that capture the meanings inside of this text. So that's whenever we say embeddings or show these boxes, that's what the embedding refers to. And that gives software the ability to compare, is this piece of text similar to this one or not, which was very difficult to do before. You could compare, does it have this word or does it not have this word? But now you can really go beyond that and create things that, systems that can understand or can do operations using the meaning behind words. So you can compare these by comparing their embeddings, and the software can get these actual results saying, okay, this is 2% similar to this one and 90% similar to this one. And based on that, you can build new capabilities into software. Embeddings can be visualized as well. So these long vectors can be shrunk and plotted into something like this. And these are messages to, let's say, a restaurant. And we can see that questions about opening hours would cluster towards the top left. Questions about the menu would cluster toward the center. And then questions about delivery and takeout cluster to the bottom right. And there's a very interesting area for me personally. I can show you a few examples of some of the things that you can do around this. This idea of similarity can be thought of as a way to create very simple chatbots, which is, if we get a question, do we have this question answered in our FAQ or not? And the very simple schematic is, we get a question, we embed it, we compare the embedding of that question with the embeddings of our FAQ questions. If we have a high similarity, okay, we identified the question, just pipe its answer back out to the user. So that's a very simple form of question, let's say, frequently asked questions. On the slightly more technical level, semantic search or neural search, there are two major ways that large language models operate in these kinds of problems. The first one, and we believe this is the one that Google was referring to in that blog post, is this idea of re-ranking. So they would have their previous technology go and search for the query, give you the top 1,000 results. And then those 1,000 results are given to a language model that says, okay, result number 50, no, that should be number 1. And result number 100, that should be number 2. And that's where the language model is called a re-ranker. And so that's one of the main family of applications of language models. The other one relies on just the embeddings. So you have a text archive, you embed all of that text. When you get a new query, you embed your query and just retrieve its neighbors. Give me the closest ones to this. That's the second idea called dense retrieval. This is a really good book that walks you through the long history of 3 years of semantic search. It's growing super quickly. It's an exciting area. We can go through some examples. Let's see if I have. So you can go to Cohere notebooks. These are public Jupyter notebooks. So you can try a lot of this code in. This is a quick semantic search example where we have an archive, we have a query, and we do the search. It starts basically by installing a couple of libraries. Annoy, this is the search library. It's an open source library from Spotify. You put your API key here, you load this data set. So this is a data set of questions. So these texts are all questions. This is the Trek data set. It's an open data set. We get 1,000 of these. And then the first thing we do is we embed them. So we turn this archive from text into an archive of embeddings. And then here we can see, okay, we have 1,000 texts. Each one of them is in 4,000 dimensions. Let's create a search index. So we throw all of these embeddings, all 1,000, at the search, the vector search database or package, Annoy, and it builds this. And then now we have our search index. Now we can say, okay, Question number 92, what are the nearest neighbors? If I'm to search for question 92, which is this one, what are bear and bull markets? And these would be the results. So what animals do you find in the stock market? What does NASDAQ stand for? What are equity securities? Notice that this talks about bear and bull markets, and that led the model to think about the financial sector. It understood that this is not specifically about animals, this is about finance. You can do the same thing with any query that you write. So you can write whatever text you want, you embed that, you search for it, and you get the results. So if we ask, what is the tallest mountain in the world? These are all the other similar questions in the data set. What is the name of the tallest mountain in the world? What is the highest mountain in the world? And so on and so forth. And a lot of other mountain questions. What I really love is to take this to the next level and just visualize the whole archive, to visualize all 1,000 and have them clustered by meaning. So you can access this notebook and sort of explore it kind of like this, and you see what questions and how they cluster together. So this is notebook number, let's say, 3 here. We take it to the next level in this one, notebook number 7. So this is where we get another data set. So this is Hacker News headlines. So these are titles for news stories. We do the same thing. We get the texts, we embed them, we build the archive, and then we visualize them the same way. But these are 3,000 points, and I don't think it makes a lot of sense to expect users to touch all 3,000 points. So how can we visually put more information there? So we do this by clustering. So we cluster it into 8 different groups, and you can extract the keywords that are relevant for each group. So you see this is about open source and kind of... so there's another way to explore embeddings through clustering and grouping, and you can find this in notebook number 7. Okay, another really exciting area as well is generation plus semantic search. These are 2 papers, 2 models. One is called GenQ, is a method for improving semantic search using generation models. InParse is another one. This is by Zeta Alpha and a company. We have Jakob here. So this is an Amsterdam-based company focused on NLP that produced this method, this InParse. And if I'm correct, maybe Rodrigo, the last author there, is one of the people who wrote that first Google paper, Monobert, if I'm not mistaken. How this improves semantic search is by, you get a document, you present to the generative model saying, okay, this is a document, generate a question about this. And that augments your data set, and you can have much better semantic search models. Thank you for bearing with me so far. A very quick summary for some of the main concepts around using language models. So we can use them for generation, for classification, for embedding, and for semantic search. For embeddings, we turn the text into numbers. We can compare those with other texts or vectors. We can plot them and visualize them and explore them that way. For generation, we have a prompt. There's a way of writing the best prompts for our use case. We should have the model generate a few of them, and then we can choose the best ones. 2 ways of creating high performance text classifiers. We talked about few-shot. We talked about this idea of fine-tuning. That is the book, Cohere AI, and that's the notebook. I would really love if you send me any feedback on the talk at that link below. Please join our Discord. That is the book on semantic search that is very useful. This is the book that the model recommended. I have never read this book. It sounds really interesting. I am going out and getting it. But there it is if you think it's interesting. Thank you so much.
Hello? Is it working? Quick question. There are several transformers and BERT-based models out there. These prompt engineer you recommended are general for them or more suited for the Cohere models?
Yeah, so different models would work on, you'd try different prompts to work on them. And the main maybe distinction between them, the two families of types of prompts, is the in-context prompt, where you show 3, 4 examples and have the model continue it, or the instruct prompt, where the prompt is something like write an article about something, where it's like, and then you have anything that you fine-tune. So you can change however you want to prompt by fine-tuning your own model. But these are generally the two groups. And across managed providers, you might have to try to change things a little bit and see what works across services. My pleasure.
Yeah, thanks for the great talk. I'm curious how speech ties into this language model. Like, obviously, a lot of human communication occurs through audio,
yes,
speech. And do you think there is information in speech that will help build even better language models, or is it mainly a deterrent and should we convert from speech to text and go from there?
Yeah, I know that's an absolutely great question. So as we talk about multimodal, so text and images, text and video, text and audio is probably one of the most important things that we should tackle. And this can be done in, there are multiple ways to do this. So there are already systems that would have a text or voice-to-text system, and then that text would go through a language model, and you do the classification or do the generation, and then turn it back into. So it can be used as a pipeline of just speech recognition into text, and then text into language model. And then there are models that are just working on language through audio directly. So Audio LM is one recent paper that just does language modeling through audio. Really excited to see a lot more multimodal work there, because that serves a lot of languages that are not, where the written language is a little bit different from how people speak it. A lot of African languages, Arabic is kind of like that as well. And so that will help a lot of that long tail of some of these languages where people speak in a different way than they write. Thank you.
Hi, I wanted to ask a question regarding your thoughts on, obviously the research on language models is very much making them bigger and bigger and bigger because they obviously perform better. But do you think that's going to continue in the sense that it's quite complicated for companies to be able to actually access these models because of obviously how big they are and hosting them tends to be quite expensive? So just your overall thoughts on that matter.
So I'm really excited about ideas that could make smaller models better. And a lot of it is information compression. So how much information are we expecting this model to do, to have? And what we sort of realized more and more like recently is that when you train a 200 billion parameter model and you expect it to memorize the whole internet, that is not the most efficient system for retrieval. You should not load your entire database on GPU memory and sort of we have better systems. We have really good databases that should be doing that. We have the internet. So I think one area where I'm really excited about the progress of smaller models aided by internet search, hopefully from credible sources. So not just search the open internet, but like search specific sort of, I think that's definitely one of the ways forward, where the language model only focuses on language information, not storing all of the information of the world. So Retro from DeepMind is one model like this. Memorizing Transformer is another model that does this. WebGPT as well. And we have a chatbot that chains Cohere's models in a way that does this. You ask it a question, it'll go search the web, give you a result. So it's not stored on it. And you can interact with that model on our Discord. Yeah, thanks.
Yeah, thanks for the talk. You said a couple of times today we should not rely on facts from language model, but instead we need kind of a retrieving model. And right now you also said like we should kind of query the internet for that. But in reality, the facts are often stored in kind of a database or so. How would you set up a problem like that to get the data from a database and then feed them in a language model for text generation? Is there something out there already?
Yeah, so the models I mentioned do that. So Retro from DeepMind Memorizing Transformer does that, and WebGPT does it via search, via web search. But what the Retro does is, they have a large database of key and value, and the keys are embeddings, and they just do that lookup of, they get the prompt, they do the lookup in the database, they get 3 or 4 results, and they pipe them back in. The database here is not very structured, so it's not like building a SQL query. It's like, what other text is similar to this? Retrieve it from the internet, but also bring the following sentences to it, because that usually has some of that information. So yeah, retrieval, these are some of the ways. And there's work on language models that can query tables that I think also sort of factors into this. So retrieval is, all of these papers that I mentioned were just December. So this is super new. Any other questions? One more here.
Hi, thank you for your talk. So you mentioned that with few-shot learning, like you can get okay results, and then fine-tuning, of course, if you have hundreds of thousands of examples, that's much better. In reality, clients usually give you like enough examples for few-shot iterations. So do you have any experiences with using techniques like weak supervision to go from a few-shot samples to maybe generating like more valid samples?
True, yeah, that's one of the, exactly, one of the methods that can be used. So maybe you can use the few-shot approach not to build the final thing, but to generate more data to be able to fine-tune, especially if you have somebody verify and validate and go over the generated examples and make sure that, and it sort of maybe helps labelers as well, where a labeler does not have to add an answer for each one, but the labeler is just double-checking a soft supervised classification that a previous model has done before. And that's another similar tactic that is done for how to reduce the cost of a language model. So you have the large, expensive model, create the data set, and then you can fine-tune a smaller model to do that. So some of the companies that are building these and they come across that cost barrier, we advise them to think about that. How can you use the big model to generate the data set and then fine-tune a smaller model that can be faster, but also more cost-effective? That's a great point. Thank you for raising it. Yeah.
So yeah, great talk. Is there also a role for explainability in these text models? So what do you think about that topic in particular?
Yeah, that's an important one. Machine learning as a whole needs to really provide better and better sort of explainability models. There's a lot of, one of the more recent interesting works in this space is, I think, called Talk2 model. So this is a paper on explainability where, let's say, a doctor who gets a recommendation from a model can have that same conversation that we saw with the DeepMind Flamingo, have it with the model, but also retrieve facts about, what features did you rely on? You're saying this diagnosis is based on this level of blood pressure. How much does, let's say, other factors need to change to do that? So this is one of the more recent sort of ways in using language models as an interface for explainability. There's a lot of work in how to use other sort of models like LIME, like SHAP, like methods, like integrated gradients that point to the model made this recommendation or this classification based on this. We do still need a lot more focus and a lot more sort of work in explainability, but it's a fascinating. I've created a cheat sheet for explainability methods. It's on my blog. Hopefully it's useful, but I keep my eyes closed on that topic. Thank you. We have one more there.
Thanks, great talk. Do you think that ontologies are still needed, or do we not need this technology anymore because of language models?
I am not educated enough to answer that. I don't know. It's a little bit, farther from areas that I've focused on. Deep learning has been a little bit surprising in terms of 10 years ago, if you were to write something that does this, you had to write a lot of the code yourself, and it had to be a 500,000 line of code program. While now it's 200 lines of PyTorch in massive amount of data, and through some explainability techniques, we have some indication that the model is discovering a lot of these rules itself. So something like BERT in like layer 2 or layer 3 is learning how to assign, is this token a noun or a verb? Is this, where these things used to be sort of done previously by hand. We're more and more exploring that these are things that the model sort of picks up from the data. So yeah, that's I think as far as I can tackle that. I hope it's useful. Yes, please.
Sorry to go again. I think my question is just, what would be your advice when you basically have to deal with data that comes in, say, 35 different languages? What would be sort of like your advice regarding how to help improve that?
Yeah. So that's one area exactly where these models. So I talked about large language models. Some of these providers just focus on one language, and some focus on others. There are great multilingual models that do this. A lot of them are open source. That seems to be an area where a lot of this can work. You have this trade-off, right? You have a model for each language that will generally do better than a multimodal, or do you do the multimodal? It's this trade-off about, I think, that in the end, it's an engineering sort of decision that has to be done. A lot of the generation models I've seen, I haven't seen many multilingual ones that do all the languages sort of well. All tend to focus on English first, and then maybe grow to other languages. But on the embedding side, which powers semantic search, which powers classification, I think there's a lot of great work of multilingual models. Thank you.
You were talking about the multimodal approaches, so I was wondering, you mentioned OCR and language models, and there are also approaches where you skip the OCR part and you directly train on pixels. I was wondering, do you think it's more promising to perfectionize each task separately or go fully end-to-end? And yeah.
So, I mean, there are some surprising capabilities that come up. One thing is, I think, CLIP, where there was this emerging property that it kind of does OCR without being specifically trained on it. You saw that, maybe you saw that image of an apple with a sign on front of it, and the sign says iPod, and it's classified as an iPod, not as an Apple. It just read that. So that's an emerging property that sort of came, and it was quite surprising at the time. I think it would really depend on the use case. That's the most common answer, I think, in machine learning. It depends. Amazing. Thank you so much. Great to be seeing you.